Eastern Pacific Cloud Aerosol Precipitation Experiment. And, you know, in the sake of this, for the sake of pointing out that this was a weird year, as far as I know, this is the first experiment to be entirely planned remotely during COVID. So that's but hopefully the experiment itself will not be remote. So it is a deployment of the AMF-1 from February 2023 through January 2024 in La Jolla, California, at both the Scripps Pier, which is shown here, and a secondary site called Mount Soledad that's just a little bit inland. Feel free to contact me by email for any questions. And I think Johannes has added to the chat the link to the slides. And so I will also have some links in the slides, so you'll have to first link to the slides to link to those. I want to point out that this was a huge collaboration and possibly more diverse than usual because it was on Zoom and we weren't biased by who was nearby. So we reached out to a number of people who are listed here, and you may recognize that there's both some measurement experts on both the aerosol side and the cloud side, and a number of folks focusing on modeling. And I'll say more about why that is. While we did get this project started, we are welcome to contributions from others. This is not a closed circle. We do, in fact, already hope to have collaborations with the NOAA Aroma program during part of this experiment that will include flights and a focus on DMS chemistry. So where is La Jolla? In case you don't know, it's approximately the pink dot. And why is what's the rest of this? So the blue area is some of the highest daytime stratocumulus cloud amount that is present on the planet. And it's, you know, there's of course 3 areas of high daytime stratocumulus between the Eastern North Pacific, the Eastern South Pacific, and the Eastern South Atlantic. We're focusing on one, and San Diego lies right on the coast at sort of the edge, the top edge of that upwelling zone that gives us that persistent stratocumulus. But one of the things that's super interesting, and this is just a GOES image recently that we put together as we were working on the science plan. And what you can see is that this persistent stratocumulus often dissipates as it hits the coast. This is a well-known phenomenon, but one of the things that this provides a pretty unique opportunity to is to understand that dissipation process and what triggers it. And so, as well as to understand the characteristics of the clouds that are coming in from the ocean and those marine boundary layers that control them. And so we expect to have both a local point of observation of that across that transition, plus the scanning instruments will give us a wider field of view that will allow us to see how the clouds change as they approach the coast and hit the coastline. And so those are the main goals on the cloud side. On the aerosol side, while La Jolla is also a marine site, it is often influenced by relatively clean marine air from approximately La Jolla. It turns out the prevailing winds are mostly northwesterlies, and those come relatively directly from the ports of Los Angeles and Long Beach, which are located here and shown in the diagram. And so, and it turns out that this provides a super interesting observational platform for looking at aerosol chemistry, because during the transit from LA Long Beach to La Jolla, there's about 12 to 24 hours or sometimes slightly more. And that is either over ocean and possibly under cloud. And so you either get a fair amount of photochemistry and clear air or a fair amount of cloud processing, and not a lot of additional sources on the way down, just because that's they don't mix with the onshore sources during that time. And so although there are continuous onshore offshore flow that also give you a fair amount of homogeneity, This gives us a way to look at downwind emissions that are relatively homogeneous, allowing us to not just look at snapshots of a plume, but relatively continuous and repeatable characteristics of urban plumes as they're advected offshore. And if you think about it, given the number of coastal megacities, there's a lot of our ocean that tends to be affected by plumes that are transported downwind over the ocean and in some cases to other populated areas. And so that's our focus here. And here's a paper with measurements from the Scripps Pier in 2011 that we did. And you can see, well, the northwesterlies are quite common. You also sometimes get northeasterlies and occasional southerly back trajectories. And if you separate those out, you can also see a pretty strong diurnal cycle in the aerosol, especially in this case during August. And so this is the target of one of our intensives that we're calling the Epcape radiation intensive, both in terms of the radiative effects on aerosol as well as the radiative effects of clouds. The clouds during this time tend to be slightly higher over a few hundred meters and still affect the radiation balance, but not in quite the same way as I'll show for slightly earlier in the season, which I'll get to. So that has focused mostly on some of our Epcape science questions, which are the cloud and aerosol climatology, understanding what the aerosol concentrations are chemically as well as physically and size-wise, as well as understanding the clouds and how they change seasonally and diurnally. And the diurnal cycle of clouds offshore has been studied by a number of large programs, including DICOMS 1 and 2. But what our focus here will be at the coastal interface and how those diurnal properties change. And I'll say a little bit about that. We're also very interested in cloud radiative fluxes, both in terms of their changes in direct to diffuse radiation. And there's a fair amount of interest because of inland solar farms as to being able to predict those changes in cloud radiative fluxes. And so we have a number of collaborations that are going to bridge that interface as well. And then finally, aerosol-cloud interactions, because we can characterize the aerosol well and because it has repeated characteristics, it provides a great opportunity with some relatively repeatable clouds to retrieve statistics on cloud properties and to link between the cloud properties and the regional signatures of the aerosols. So those are our three target questions. This is the Scripps Pier. It's pretty long, as you can see. So in addition to the boats that are parked here for use getting lowered off the pier to take samples, there's room at the end for the AOS, the Aerosol Observing System van, and then space for vans on the north side, probably about mid-pier here. And the roof of this pump house, which is also where water is pumped up the hill for analysis, as well as trace gases are analyzed, is going to also serve as a potential location for ceilometers and other upward-looking instruments that don't go inside the arm vans. And you can hear more about this in the poster that David Chu and Heath Powers are presenting, and I'm not sure what session that's in. So that's the basic layout. There's already a lot of infrastructure on the pier, including it appears to be sufficient power. We expect to put the radiometers off. If you see the boom in the northwest corner here, as well as the E-core, there's actually already a correlation flux instrument on the southwest boom, but we think we can add ours to the northwest boom and do comparisons, as well as put radiometers out there to be downward looking over the ocean. And so there's a number, and of course the pier provides security as well as shared use. And so it is open to shared use from other investigators. We are, the permanent installations that require real estate are the thing that we'd like to know ahead of time, because that allows us to get approval ahead of time for them. So while it is a Scripps facility, there are restrictions by local entities, including the Coastal Commission, that we are requesting. So if you have interest, please do let us know. We're open to that. In addition to the pier down here in the top left, the secondary site is Mount Soledad, which is shown in the bottom middle here. And it's about 1.5 kilometers from the pier to the mountain, and it's about 250 meters up. It's not quite on the top of the mountain where the site is. And I'll show you some pictures from approximately this yellow dot here in a minute to show you that the cloud is frequently in June in cloud. And so our hope is that we can both put the SACR up on the mountain and other things that want a longer field of view to be able to get further out on the horizon, as well as to put some cloud chemistry up there to compare to the pier and to measure during clouds. So here's a recent morning during my dog walk. And you can see on this morning, it was actually pretty clear just before 7 a.m. And then a cloud started building in, and by half an hour later, it was pretty well socked in. The mountain up there was enclosed in cloud. And then just a few other examples from this month. I think the building in was somewhat unusual. I think the more typical pattern has been that the clouds build in at night and then dissipate in the morning. And so that's more of the coastal cloud system that you might expect. But we do expect to have during April to June, especially in-cloud sampling at that site. So we will have droplet measurements provided by Environment Canada and a CDI from them as well, in order to sample at that site the chemical composition by mass spectrometry and size distributions of the cloud drop residuals that are evaporated. And Marcus Pettis will tell you more about that. This is the UCSD site at Mount Soledad with space for 3 bands. There's 2 condemned old laboratories that are suffering from asbestos-related issues. And just to wrap up, what we're getting to next are science highlight talks, and I see I have 2 minutes left. And I guess my dog is telling me that too. So Susannah Burrows is going to tell us from the modeling perspective, opportunities to better understand E3SM, aerosol, and CCN using Epcape observation. And Allison Aiken is going to come from the observational perspective to talk about aerosol sources in the coastal marine environment. Mark Miller is going to give us the perspectives on turbulence and drizzle and coastal stratocumulus, and Dan Lubin will focus on Southern California cloud radiative properties. And then Marcus Pettis will talk about questions of cloud chemistry using that Soledad site, or how we expect to use that Soledad site. And Matt Christensen will give us a perspective on indirect radiative effects of aerosols. And Mikael Witte will talk about the Lagrangian observations of interactions of aerosols, clouds, and near coastal circulations that we could use in this project, and that we plan and propose to use as part of Epcape. So questions and contributions are welcome. That's my main message. And if anything we don't get today, just email me. You can also add to the Slate. Slack channel for questions. This should be the link. The slides from this presentation, you probably have to get the link from the chat in order to get here. And then the Epcape draft science plan is posted here. The official one will be published at a later date. So that's all I've got. And we should jump into the science highlights now. And I'm gonna hand it over to Johannes Mummenstadt and D.A. Wang to moderate for us. And then we'll come back to questions during the discussion section at 12:15. Thanks.
Yeah, thank you, Lynn. So we have a couple of science highlights in the rest of the session. So our first speaker is Mike Christensen, and the topic is Lagrangian perspective on the indirect radiative effect of aerosols. So Mike, please share your slides.
Okay. Okay, can everyone hear me and see my slides?
Yeah, so you may want to put in a presentation mode.
Is that better? Does that work?
Yeah, take it away.
Okay. Great, thank you. So thanks for this opportunity to talk about the Lagrangian perspective of analyzing aerosol clouds and evolving systems. This work was carried out by Johannes Momestad, Adam Varbel, and Jerome Fast. And so here we're going to ask why a Lagrangian perspective. And the main reason essentially is that when we consider processes like the Toomey effect, we're looking at clouds that undergo instantaneous changes as you add aerosol to the system, meaning that the liquid water path is considered constant as we look at a microphysical transformation. But we know in reality that clouds evolve over time. And as they evolve, they undergo different processes such as changes in precipitation or evaporation. And this can change the liquid water path. And we know from several LES experiments over the years and data observations that indeed aerosols can increase cloud droplet number concentrations and actually affect the drizzle process and the evaporation. And so therefore, we need to put this into the context of a time evolving system where we can monitor the changes not only in cloud droplet concentration, but changes in liquid water path and cloud fraction as we change the aerosol loading. And so the approach here is to combine the ARM data from the ENA site in the North Atlantic with satellite observations so we can quantify the strength of time-dependent relationships between aerosol and cloud properties for warm clouds, and then use these relationships to evaluate sort of like a climate model like E3SM. And so essentially, these are the data products that I'm going to be using and describing in this research. So several ARM quantities from this ENA site, such as the cloud condensation nuclei, which is a very useful variable so we can connect these clouds to an aerosol change, as opposed to using just the satellite aerosol optical depth, which has been predominantly used in the past to look at aerosol radiative forcing from satellite observations. So the idea is to connect these sort of Eulerian observations from the ARM with the Lagrangian from the satellite. So in Eulerian, we just have clouds that sort of pass over the site, but in Lagrangian, we can sort of connect these initial observations that are very detailed from ARM, and then look at how the cloud system evolves in time using geostationary satellite observations, and then compare these sort of to a model to see how well it behaves in the time domain. And so just sort of an example, we're going to use the high split model with MERA2 to look at trajectories, both backwards and forwards from the ARM ENA site. And this is just sort of showing an example of, we have a bunch of these open cellular clouds that are sort of drifting over the site and sort of bursting precipitation that's measured by the ground-based radar. And we can track these clouds over 48 hours to sort of see how the system evolves in time, and then look at an ensemble of cases to look at how these cloud systems respond in general loading, differences in aerosol loading. So in total, we have about 650 trajectories that are going into this study, and we have a trajectory that's initialized every day at noon, and we build these up over a course of about 2.5 years. And this leads to a distribution in the CCN, the cloud condensation nuclei at 0.2% supersaturation, a histogram that is shown in the right-hand panel here. So that for the ARM observations, we can see that the median of the distribution is about 113 per cubic centimeters. We can also do a simulation with the E3SM model nudged with MERA2 as well, and it picks out a similar PDF of the distribution. And you can see quite clearly in the time series over 2.5 years that there's a seasonal cycle in the CCN, having higher values typically in summer and lower values in winter. The lower values are in winter typically because you get more of these frontal systems that move through and wash out the atmosphere and deplete CCN, whereas in the summer, fewer of these events occur. And so the next step now is to look at how do the cloud properties look in a Lagrangian framework. So what we're going to do here is take all of the trajectories at time t equals 0 and classify them as either being clean or polluted strictly based on the CCN that's measured at the arm site. So if the value is greater than this median value of 113, the whole trajectory is considered polluted. If it's less than that, it's considered clean. And so this sort of works as an analogous concept to this Epcape concept, where if you're looking at trajectories from this pier, perhaps you can utilize a Lagrangian approach to sort of look at what do the cloud properties look like an hour later, 2 hours later, 6 hours later, a whole day later, for example, from the advection of the winds that are moving this aerosol out over the ocean. And so an initial analysis of comparing sort of the aerosol optical depth as retrieved from MODIS, the satellite instrument, with the arm observed aerosol optical depth, what we observe is that when the CCN is higher than the median, you tend to observe higher aerosol optical depths. And this is a quite intriguing result because it implies that, yes, indeed, this whole column loading AOD of the atmosphere is a fairly decent proxy for the abundance of CCN. There is a correlation here at time t equals 0 at the initial time of these Lagrangian trajectories. And we see this also in the ARM and MODIS observations, as well as in the E3SM model. Interestingly, the MERA2 response is a bit smaller, but it is on average a bit, the AOD is a bit higher in the MERA2 model when the ARM CCN is greater than 113. And what we also see is that as these trajectories move out over the ocean from the ENA site, this response tends to be fairly strong over multiple hours and even out to a couple days. So if you start off with higher CCN, your AOD is going to also start, but it's going to continue to remain high for a couple of days at least. So now we can ask the question, well, what do the cloud properties look like at the initial time of the Lagrangian trajectory, and do they change over time? And so one parameter that's often used to look at aerosol indirect effect is the cloud droplet effect. And this is a measure of how large the droplets are in the clouds. And what we see is that when the aerosol, when the CCN is higher than normal, we tend to observe smaller droplet sizes in the ARM observations from the multi-shadow rod radiometer. And interestingly, it agrees fairly well with the cloud top retrieved droplet effective radius from MODIS at sort of the time t equals 0 of this Lagrangian trajectory. The E3SM model is also showing some skill in representing a smaller droplet size under more polluted conditions, but there's an overall bias that we're currently looking into at this E3SM site. And then this other series product that provides hourly 1 degree resolution cloud property data is also showing a decrease, although there is a significant bias in that data set as well. So overall, all these products are indeed showing that there's a smaller size in the droplets, higher CCN, ARM measured CCN, but there's some biases between them, which requires a bit further investigation to understand. Nevertheless, what one can do is then look at, well, what do the clouds look like a full day later? So between time steps 20 and 30, we can still see that when we've started off with higher than median CCN, that there's still some memory left in the system a full day later, that the cloud droplet sizes are significantly smaller in all of these products. Obviously, we don't have ARM a day later because this is in a moving framework and we're far away from the ENA site at that point. And then by
minute and a half left.
Okay, thanks, Johannes. Okay, so I'm just going to try and quickly wrap up. So when we look at cloud droplet concentrations, we see a similar story, except higher CDNC under polluted conditions, and there is memory in the system, we see responses a full day later. The liquid water path and cloud fraction adjustments are actually negative, which is something we're looking at right now to try and understand. And initially we were thinking that maybe perhaps aerosols are not suppressing precipitation, and that's why the liquid water path is decreasing. But indeed, the aerosol does reduce rain rates. So there could be other processes such as cloud top entrainment that's leading to these negative adjustments in liquid water path and cloud fraction. And so the next steps now are to do more stratification by different meteorological regimes, lower tropospheric stability, relative humidity, and so on, and to look at other sites around the world, such as the Southern Great Plains and the California Stratocumulus stack, to test some of these hypotheses. And there will be a poster between 3 and 4 today looking more at deep convection in the Lagrangian framework. So thank you very much.
Great, thank you, Matt, and thanks for being right on time. So in the interest of time, please put your questions to Matt in the chat, and we've designed the session so that there's plenty of discussion time at the end. So next up, we have Markus Petters telling us about cloud chemistry. Looks good.
Right. Looks good? Okay.
Yep.
So Lynn asked me to talk a little bit about the cloud chemistry question during Epcape CFCC. So this is a collaboration between Lynn, Suzanne Paulson at UCLA, and myself, and this is currently proposed. And so the idea goes back to that of the Hoppel paper in 1986, who first reported the effect of precipitation, like non-precipitating clouds on the aerosol size distribution. And out of this came the famous Hoppel minimum. And sort of what these observations are showing is that, what the underlying theory is that you get droplet activation, then there's some cloud chemistry kicking in that grows those droplets, and that leads to sort of a shift of the modes here of the 1s and the 2s. And you get this minimum here, which is indicative of the supersaturation that's active in the cloud. And sort of the broader picture here is that there's a tight coupling between the gas phase and droplet activation and cloud chemistry that we're still trying to understand to this day. So why do we believe that Epcape is the place to study this? So this is a satellite loop of the clear IR image from the GHOST satellite. The blue colors show you the ocean temperature here, and here is LA, and here is La Jolla, and so this is our trajectory here. And you can see the cloud actually building. This is similar to the picture that Lynn just showed us. So for some period of time, we have transects through cloud, and for some period of time, we have transects through clear air of the LA pollution plume. And if we put this in into a schematic of the observable cloud processes, this is adapted from Rob Wood's picture in MWR in 2012. So here from the left, we have the LA-LB prevailing wind and the plume coming in, and then we have the whole gamut of boundary layer processes happening in the cloudy boundary layer. The whole thing advanced to Scripps Pier, and then we have Mount Soledad sitting here on the right, and we're going to propose to sample on top here or near the top to sample the result. And sort of the key feature, and Lynn already alluded to this, is that we have a predictable measure of cloud cycling, which is some mixture of the turbulent structure of the boundary layer and the prevailing wind speed and the cloud amount that you can get from satellite. And we would expect that the aerosol plume here will go maybe up to a few tens of maybe cloud cycles before we get to sample them. So here's a picture on Mount Soledad from one of Lynn's previous deployments, and what we're thinking about is to put CVI inlet and an isokinetic inlet up on the trailer. and then have a whole slew of detailed aerosol size distribution measurements, including a DMA, a POPs, and an APS, as well as detailed CCN measurements, both from the cloud droplet residuals and from the total inlet. And then some key instruments that go towards mixing state and single particle composition is Lynn's high resolution event trigger AMS and the single particle soot photometer. There will be some gas phase measurements from the iodide SIMS. There will be some functional group composition from Lynn's filters, and we're going to look a little bit into OH bursts, which is Suzanne Paulson's probe, and I'll talk about it a little bit in the next few slides. So what are we trying to test? So the first thing we want to look at is the chemical signature of cloud processing. This figure is from a paper by Sanchez et al. From Lynn Russell's group, and what they had was below cloud measurements and in cloud measurements of aerosol composition, and also a model of partitioning of compounds into cloud. And the key finding here is the second bullet point is that the simulated cloud droplet composition contained more nitrate, salt, and less black carbon than the interstitial aerosol or the below cloud aerosol. And that is probably something that you might intuit, but the key sort of like shortcoming is that the mixing state was unknown at the time. And as we've learned yesterday, again, from Jim Smith's presentation, I believe, Zeleniuk's data is that mixing state exerts a huge influence on the retrieve cloud supersaturation and the whole Aerosol-Cloud cloud partitioning problem. So we hope that the event trigger AMS and the SP2 will help us, give us enough mixing state resolve information to really better constrain of what is produced during the in-cloud processing as the plume advects. The second hypothesis we want to look in is the influence of gas phase species on CCN activation. And the idea goes back to the 1990s when nitric acid first came up to have this effect, and then it evolved in sort of like the last decade so to include more organic species. And the example I'm showing here is from the Serene's paper from Faye McNeil's group in 2013. And what they did, they exposed ammonium sulfate aerosols in a chamber to methyl glyoxyl and acetaldehyde. And what the data show is that you see like a decrease in the critical activation diameter by up to 15% due to the exposure of those gas phase species. And the point here is that things like methyl glyoxyl and acetaldehyde, these are highly volatile gases. They're not really contributing to the amount of solute in the drop, and the mechanism here is very distinct. It's like they were thinking of some interfacial tension reduction that actually caused that drop in activation diameter. There, as I already mentioned, nitric acid, there's other semi-volatile organic vapors formed from secondary organic aerosol formation to all have sort of like the similar effect of the reduction in critical diameter. So we're thinking by somehow stripping the gas phase off, we can show that this is a process that is active in the environment. And the idea in Epcape, obviously, is that we have a great source of VOCs coming from LA. So if there is a signal, it should be quite strong in this particular environment. And the last hypothesis we sort of want to explore is this question of OH bursts. And this goes back to Suzanne Paulson's paper in Scientific Advances. And what they showed is that if you actually wet the particles, you get this burst of OH radicals. And this is a new source of OH. And so the typical sources of aqueous phase OH is either through uptake of OH from the gas phase or to aqueous phase production. And this mechanism is very different. It acts a lot faster, so it comes in after like a couple of minutes of the wetting exposure, and it actually leads to much higher OH amounts than you would traditionally think of in terms of these classical mechanisms. And the significance here is, of course, that you need OH to get the in-cloud chemistry going. And you have like multiple cloud cycles here. So we want to deploy her instrument to look at the OH burst in the context of these cloud cycles.
2 minutes left.
Yeah, I'm about to wrap up. So the last slide I have here is sort of like the synergy with the DOE Epcape deployment. And as Lynn already pointed out, the AMF1 is going to sit on the Scripps pier, and most of the remote sensors are going to sit down here. And so we're going to have a complementary set of measurements of size distribution, aerosol chemistry, CCN, and cloud droplet number concentration estimates. And the real question that I think both campaigns will benefit from is like this idea of vertical mixing of the aerosol and the aerosol properties near cloud base. So if you want to do a good aerosol to CCN to droplet closure, you need to know what's going into cloud. And obviously, if you're not well mixed vertically, then the local properties are not super meaningful. So we think that obviously the deployment will mutually benefit each other. So that's all I have. And I'm handing it back.
Yeah, thanks a lot, Marcus. So if you have questions for Marcus, please leave it in the chat and we will answer them in the discussion session. So our next speaker is Mark Miller. So he's going to talk about perspectives on turbulence and drizzle in coastal stratocumulus. Mark, please take it away.
Okay, so I thought we'd talk a little bit about turbulence and drizzle in coastal stratocumulus, and I thought I would provide a little bit of perspective from past AMF deployments in this realm. So there are 4 past AMF deployments that are relevant to Epcape. MASRAD, the first one on this list, was a 7-month deployment in Point Reyes, California. This was the first AMF deployment. It is the most relevant to Epcape itself, and I'm going to talk most about it. CAP-MBL was a 19-month deployment in Graciosa. That was a mid-latitude transition stratocumulus and led, of course, to the ultimate deployment of the ENA observatory. I'll mention that a little bit. And then the final 2 are TCAP and MAGIC. I won't talk much about those. They are relevant to this, but I'm going to focus on MASRAD mostly in the interest of time here. So MASRAD was conducted back in 2005, and here's the Point Reyes National Seashore is indicated here. San Francisco is just to the south and Monterey, and you can see the cloud cover there. So on the left-hand panel here, you see a depiction of the peninsula there, and the red circle there is approximately where the site was located. The prevailing wind was from the northwest. In the center panel here, this is sort of a graphic view. This isn't exactly when the AMF was deployed there, but this is a layout of the site itself. You'll notice it's about a half a mile from the actual surf zone, and that's going to play into something I'm going to point out a little bit later. Down here in the lower right-hand corner is a picture of the AMF1 as it existed back then. You'll notice it's much smaller. There's no Kaiser sitting there, for those of you who are familiar with that instrument. And that's because the Kaiser was not yet ready for deployment when we did this experiment back in 2005. So we had to borrow a W-band radar, and that had some issues with its reflectivity calibration. We were, however, able to get Doppler, but we did have some limitations based on equipment. That said, microphysics and radiation were still very doable. And here's some plots. Basically, this first one is a histogram of the frequency distribution of liquid water path from Microphysical 2009. And down below here is the optical thickness observed during MASRAD. And at the bottom here, these blue dashed lines on the plots are actually my interpretation of the frequency distributions from Jensen et al. 2007, which is a Modus Terra California stratus holistic view regionally, mostly during the daytime. And you can sort of see how those play into sort out. At least you can maybe see that at least at Point Reyes, it seemed like the liquid water paths were a little bit higher. and the optical thickness is a little bit higher too. Also, fire and dicoms, the green bars there are the ranges of liquid water paths observed there. So for me, when I look at this and think about Epcape, I know we're probably going to see, if it's anything like MassRad, thin stratocumulus. Adiabatic liquid water contents will probably be fairly near adiabatic and probably in the 70 to 170 gram per meter square range. Optical thickness is probably 8 to 30, light drizzle, light diurnal, large diurnal cycle with the drizzle maximum around dawn, and daytime thinning. This is your classic single layer stratocumulus evolution. Now at MassRad, we did encounter some interesting effects that may have been related to our inland location. So here's four of us put together a paper here. This is Cheng et al. 2010, in which here in the left-hand column is the standard deviation of vertical velocity. On the right-hand column is the skewness of the velocity distribution, and this is against normalized cloud depth. And I don't have time to really mention too much about it, but you'll notice the bullet points are all in red on the right, because at MassRad, we saw decreasing in-cloud turbulence with height, positive skewness at cloud top in the night and the morning. And we concluded from this, in this study, that this was primarily shear-driven turbulence. And so this was definitely modified marine stratocumulus rather than pure marine stratocumulus that we would expect over an unfettered marine boundary layer. On the bright side, if we look at number densities, cloud droplet number densities versus effective radius here, and this is sorted, these data are sorted by the fraction of back trajectories that were in the listed type here. In the upper right-hand corner of the first plot, you'll see marine. So this particular plot is mostly marine cloudiness. The red triangles there are values that were the best values in terms of not having any drizzle. And these red lines are an adiabatic cloud model with a log normal distribution exhibiting the normal 1/3 rule. You can see that generally in the marine cases, we didn't have very many. That's one message. But when there was no drizzle, basically, and this particular retrieval worked well, then these were fairly well prescribed adiabatic clouds. When it became continentally influenced, you'll notice that immediately the number distribution of cloud droplets moved towards actually the mean was 292 here. So we did see a differentiation between marine and continental air masses. But down here on the bottom, we see that most of the observations that we made at MassRad were not in either a marine or a continental environment, but rather in a mixed environment. And the green dots there, I'm sorry, are when it's drizzling a little bit, but you can still see in general the data points within uncertainty kind of fit what we would sort of expect for marine stratocumulus, except one thing that I would like to point out down here in the lower right-hand corner was that when we had very high aerosol loads, and you can see the numbers there, we also had the greatest cloud droplet number density. The bottom line from this plot, what we take away from this is doable. In other words, we can see differences in air mass and ACI in these coastal locations. Now, back then, we didn't have what we have now. This is a slide that I got from Christine Chu, and this is one of many. There are other retrieval algorithms in the program that are equally viable here. This particular one is very interesting because these days, unlike MassRad, we can get at number concentrations, water contents, the droplet size distribution, drizzle properties, and even get the associated uncertainties by using an ensemble approach, and the references are down here at the bottom. And we can basically incorporate it multispectral separation methods, basically to separate all these things out. The point being here, and this is during ACNA, we have a far greater capability now than we did during MassRad. One of the things that's also interesting that we didn't have during MassRad is the Doppler Lidar. Back then, the subcloud layer was sort of this ether that connected cloud base to the ocean surface, but there were really very few observations in between. Now, of course, we have a Doppler Lidar, and one is deployed at ENA. And these are profiles of the specific turbulent kinetic energy for day and night over 3 summers when there is no drizzle and it's very thin stratocumulus that are prescribed between 1 and 400 meters here. And what you see here, if you look, is a steady increase in specific PKE as we move upward towards cloud base, and presumably that will extend right up on into the cloud. And that is exactly what we would expect to see when we look at traditional single layer marine stratus over the marine boundary layer with no continental influence like we saw in some of the mass rad observations. The point being here that the Scripps pier probably will provide this kind of format. In other words, we'll have less land influence, a more pure view of what marine stratus look like as they do move onshore. There may be some land influence in there, but it may not be a terrible amount.
Minute and a half, Mark.
Perfect. One of the most interesting things we did during CAP MBL was the Pico Graciosa cloud optical thickness experiment. And here you see on the left hand this photograph of a broken cloud field, and off in the distance there you see this volcanic peak sticking out of the ocean, and that's Pico, and down below that cloud is Graciosa. They're separated in space, but we had radiometers on the top of Pico at a facility there and down at the surface in Graciosa. And the point I want to make here is that with this kind of setup, basically when you're measuring radiation above and below the cloud, and I think we'll have opportunities to do that in this particular experiment, you can get at the optical thickness in broken clouds. I can't show you all the retrievals we did here, but this was quite a successful thing. So to summarize here, basically, I'm not going to talk much about the top bullet point there. Just I expect, I think most of us do, sort of single layer, simplistic stratocumulus, if there ever is such a thing. But also, I am very excited about the fact that we are going to be able to characterize the surface maybe better than ever. We'll have a better look at sea salt, one of the things we really struggle at in mass rad, and the surface fluxes, I say maybe, but I'm going to switch that to almost certainly. And I think this is the first time we'll have actually surface fluxes coincident with and continuously measured at the time we're measuring marine stratus. And then of course, we can do dual Doppler things here, the Sacker and Kaiser sort of intersecting one another in a shallow boundary layer like the one we had in mass rad. So that is about all I have to say today.
Great, thank you, Mark. So questions to Mark in the chat, please, so we can come back to them during the discussion. And next up, we have Allison Aiken telling us about the coastal aerosol environment. Oh, and the cat applauding in the background.
Which I have to say, if you can hear me now, it's not my cat because I don't have one.
That's my cat.
Ah! All right, can you see my screen?
Yes, but not in presenter mode.
Yes, it's...
I mean, sorry, not in...
slideshow, yes, I knew what you meant, yes.
There we go.
All right, well, thank you everyone for joining us today, and thank you, Lynn, for the invitation to speak. I'm excited to talk about aerosol sources, optics, and mixed phase chemistry that we expect to observe during the Epcape campaign, so in the coastal marine environment. So as kind of has been brought up, I think a couple times in the meeting already, but we know that combustion aerosol sources impact the atmosphere in terms of the radiative budget and cloud formation, and ship tracks have been largely studied in terms of their impacts, but are also highly uncertain. And even more uncertain is what is the role of the large urban centers. And so that's where Epcape is going to be very interesting for us to be able to study these aerosols as they're transported from the Los Angeles and Long Beach Basin with a transport time of, as Lynn mentioned, about a half a day to a day's atmospheric transport time. And there's been previous work by Lynn's group in this area before, showing that carbonaceous aerosols dominate the submicron mass, as you can see in the table on the bottom from FTIR and aerosol mass spectrometry. This was a seasonal campaign from August to September, where the highest concentration of mass came from combustion sources, even though the measurements are being made out on the pier. And so then after that, also quite interesting is there's a significant impact from biomass burning plumes, and then also, of course, marine origin aerosols. And there was also significant observation of SOA formation and ozone chemistry during that campaign. So I've been working on aerosol sources in the Eastern North Atlantic. And one of the things that we did was during the ACE-ENA intensive operating period, we deployed a supplementary aerosol site to try to understand better the local sources that were impacting the main site, shown in orange, where the aerosol observing system was. So from the data that we collected during that period, we were able to identify, well, we were able to develop a new mathematical algorithm to identify these local sources. And some of them were from the airport, others from the nearby towns. And so these are much more nearby sources than we expect to see during Epcape. But we were able to identify these time periods in order to constrain them for either studying that period or not studying that period. But those local sources in this case were significantly impacted by the Aiken mode diameter particles that were below 100 nanometers in diameter, whereas the accumulation mode more studied and for CCN predictions were less impacted by these local sources. So it'd be interesting to see how these kinds of algorithms need to be altered, or what we see at Epcape in comparison to what we see at ENA. As you can see, also just over on the right, that's just another plot of the number of accumulation mode and the number of the total submicron aerosol, where you can see the large impact if you're looking at aerosol processes of the total submicron aerosol, but the accumulation mode is in terms of a 24-hour average, which is used more in modeling cases, is less impacted by these local sources. And there's a paper that came out on this just last year in ACP. In continuing this work, we also have been looking at identifying multi-day long-range transport events as they impact the aerosols at ENA. And this was also developed using mathematical algorithms. We could probably be doing similar things in the future using machine learning and other techniques such as that on the AOS system. We use the chemical, physical, and optical properties from the AOS data, and we're able to identify 9 different long-range transport events during 2017. And then we're able to classify them into 3 different regimes based on these aerosol properties, into a dust and marine regime, a continental mixed aerosol, and a biomass burning smoke regime, and then validate those with satellite data from NASA Calypso aerosol products. And we also did the NOAA back trajectories as well to help validate the sources of these aerosols. If you'd like to learn more about this work, please come join us at our poster on Thursday. Other questions that we have in addition to the in relation to the carbonation aerosols from the urban centers are, do models predict the absorption enhancements of black carbon over the oceans accurately? And so we would like to look at this during the Epcape campaign. And we kind of have developed a few questions that we have that we would like to look into. The first is, how do the marine sources affect the optical properties of the absorbing aerosols from like this large urban center? Does this look differently than it would over the continent? And what is the internal mixing state with the absorbing species that's including both black and brown carbon? We also are interested in, how does the marine environment enhance carbonaceous aerosols' ability to uptake water and affect cloud formation? And what are the effects of aging and mixing on the optical properties, chemistry, and ability of these particles to form CCN? So for the first question, we have developed a humidity-controlled single scalar albedometer, and there's a paper that came out earlier this year on this instrument. And so we have looked at both scattering and absorbing aerosols in the lab. In terms of for Epcape, we would like to look at internal mixtures of both absorbing and scattering species. So a mixture of, say, inorganic sea salts, and we can mix those with other absorbing aerosols, black and brown carbonaceous species, to look at how the single scattering albedo changes and the absorption changes with relative humidity. And then we can use these empirical measurements both in the lab and then also, if deployed to the field, could use them in models to enhance the functional use in models. The second question, in terms of how does the marine aerosol internally mix with the black and brown carbon? Historically, we've looked at the biomass burning plumes. Most of those have been over the continent. We've of course observed them at ENA as well, but we've studied more the ones over the continent and are interested to see how those might be different if you've got a wildfire plume that actually was aged over the marine atmosphere in Epcape. However, maybe we would get more that would actually have just come straight from the continent. I'm not sure actually where all the sources of wildfires are that we might see during Epcape. So this will be quite interesting to compare with the measurements that here we're showing that were all collected over the continent, where we see a coating enhancement on the black carbon and a more oxidation towards the edges of the plumes. There's a paper that came out on this in 2019 and also new upcoming work as well.
1 minute.
All right, I better speed up. And so then just quickly for the last question, in terms of how does the marine environment enhance the carbonaceous aerosol's ability to uptake water and affect cloud formation? We've simulated some inorganic mixtures of salts, and we can compare those measurements with the humidified CAPS measurements as I showed earlier. We can also look at aging effects on the optical properties, and we've done that with some carbonaceous brown carbon mimics in the laboratory so far. If you'd like more information on that, please see the poster this afternoon. We also are preparing for the tracer campaign. It's called the Tracer Carbonaceous Aerosol Thrust, and we will be deploying a container with an inlet stack designed similar to the new AOS containers that ARM has. So this is a capability that could potentially be used here as well, since those campaigns do not overlap. And with that, I would like to thank everybody for your attention and just put up a slide with all of my colleagues and thank them in the Center for Solid Forensic Experiments at Los Alamos.
Thanks a lot, Allison. That was a great talk. So I want to introduce the next speaker, Mikael Witte. So his talk is about Lagrangian observations of interactions of aerosol clouds and near coastal circulations. So Mikael, the floor is yours.
Great, thank you. Thanks to Lynn and the rest of the organizers for inviting me today. So I'd like to talk today about an aircraft campaign we're starting to put together. This is in collaboration with Anthony Buchholz at NPS, who runs the NPS Twin Otter, and Patrick Chuang at UC Santa Cruz. So as I said, we're putting together plans for a flight campaign that we're proposing to ONR. And today I'm mostly just going to try and go through the aims and motivation and maybe solicit some feedback from you and hopefully your participation. So the two main goals of the aircraft sampling are going to be, one, to sample upwind of the AMF site on the La Jolla Pier to constrain evolution of the air mass that's arriving at that site as it travels from LA and Long Beach to the southeast. And then a secondary question, and I think this was actually brought up in the chat, is there an aerosol source term due to near coastal circulation? And I think this is a really interesting thing to get at because of how complicated the flow can be. So for those of you who aren't familiar with the aircraft I'm talking about, this is the Twin Otter. You can see a picture of it right there. This used to be known as the Surpass Twin Otter. It's now an externally funded lab in the NPS Department of Meteorology. This is a plane that's great for sampling the planetary boundary layer in low clouds. It doesn't have as long of a range as, say, the NCAR G5, but it is great for doing low flying. standard with this aircraft, we've got basic thermodynamic, turbulence, microphysics, and aerosol instrumentation, as well as some radiometers, which is Anthony's specialty. And then for this project, we're working on getting some additional aerosol instrumentation from colleagues at the Naval Research Lab in Monterey. And if you are interested in flying an instrument of yours, please contact me. We have a few openings for remote sensors in particular, which I'd really like to get in on here. So if you have one for hire, feel free to follow up. So I'll show this figure again for about the fifth time today. But basically the idea here is we've got, get my laser pointer, we've got this prevailing wind carrying all of the pollution from the ports of Los Angeles and Long Beach along the coastline down to the Epcape site at the La Jolla Pier. So the aircraft measurements that we'll take will give us context on evolution of that air as a function of surface fluxes, cloud processes, and circulations, essentially land sea breeze and the low level of jet along the coast. And specifically, we'd like to get at whether there is aerosol transport across the marine boundary layer capping inversion. So to go back a few years to a paper from Alt et al., they did back trajectories of air arriving at the Scripps Pier during regional pollution events. And what they found is that many of these trajectories just kind of tracked right along the coastline here. And so this is what we'd hope to sample. And then some also were spent a little bit of time over land before coming back out to the ocean. But I think the point here is that when these trajectories are so close to the coastline, the diurnal cycle of land sea breeze circulations could imply perhaps a land-sourced aerosol source that can be advected over the nearshore and marine boundary layer. And if there's any transport happening, that would be really helpful for us to know, to kind of get away from this assumption that we just have unmodified transport directly from Long Beach in LA. And to get at this now from maybe more of a vertical view of things, we know that there's evidence for PBL transport from the LA basin from a lot of lab studies and field campaigns, but there's not as much on the coastal circulation south of the Catalina Eddy, which we're kind of, Catalina Eddy is more happening up in this region, and we're trying to look a little bit farther south. So there's really just not that much in terms of observations from aircraft in this area. And if we think about the traditional view of coastal circulation, it tends to be biased towards Northern California, where we have a lot more coastal topography. We're thinking like Big Sur or farther north along the Mendocino coast, where the coastal mountains can get up to well over a kilometer and approaching 2 kilometers, 5,000 to 6,000 feet. And so there's a much stronger constraint in terms of how far marine air can intrude in the coastal areas, and conversely, how much the continental air can be pulled out over the sea. So if we're thinking about Orange County and San Diego County, we've got much lower topography, which here I've just shown as flat. But for the maximum really is less than 400 meters. So we've got much weaker coastal topography, and this means that we can have perhaps an enhanced role of sea land breeze circulations. And you can see this in this figure from Ron and Mitchell, where they looked at aircraft soundings at various airports in Southern California. Here I'm just showing their figure showing the San Diego sounding, and then balloon soundings at the Miramar Marine Air Base, which I think is about 15 kilometers inland. I may be confusing kilometers and miles, but either way, this is just a few kilometers inland. And you can see here at 0 UTC, which corresponds to about 5 p.m. local time, we have a much higher inversion inland. And so you can see that there's some evidence that there's probably some sort of sea land breeze circulation happening here. And the big question is, of this polluted return flow, where we're advecting all of the emissions, combustion emissions from the populated coastal areas, what is the amount of aerosol that we're actually pulling back into the boundary layer as the evening commences and we have a change in the boundary layer structure. So in terms of flight planning, the main idea here is that we'll be doing Lagrangian sampling upwind, and this is targeted for the April to June intensive observation period, which I don't know if Lynn talked to, but this is during the Stratocumulus maximum during the year. And as you can see from this map, this is a complicated airspace for a number of reasons. There's a large coastal population in Orange County, as well down in the San Diego area. And then in between, there's a big military presence at Camp Pendleton. And all along in between, there's heavy civilian air and ship traffic. So there are definitely going to be some constraints on how low and high we can fly, depending on exactly where we are trying to sample. That said, to return now to this schematic, the basic idea here will be to do kind of a drift with the mean wind across some cross section. It can either just be tacking back and forth, or it can be more of a drifting spiral. But either way, the idea here will be to just sample with deep sawtooths in the vertical from surface to free troposphere, so we can sample both the below cloud aerosol population as well as what's above the inversion. And so this will be a little bit similar to the post campaign, if any of you are familiar with that, except instead of just focusing on the inversion layer, we will really try and get the entire boundary layer up to the free troposphere. So this means we won't spend a ton of time in any single area of the boundary layer and try and comprehensively sample as much as we can so that we understand what's arriving at the La Jolla site. So to wrap up, we've got planning underway for an NPS Twin Otter campaign during the April to June IOP, with major goals being to understand air mass evolution and constrain any aerosol transport through the inversion due to near coastal circulations. If you'd like to get involved, please get in touch with me. Here's my email address, and you can find this in the slides, I think, that are posted online. So thanks, and look forward to any of your questions.
Great, thank you. So again, we'll save the questions for the chat and for discussion. And next up, we have Susannah Burrows talking about how to use Epcape data to understand model biases.
Great. Can you hear me? Does the sound okay?
Yep, sounds good.
Great.
And slides
Thanks.
are good too.
Are you seeing the presenter mode?
Nope, we're seeing what we should be seeing.
Oh, okay. Whoops. Well, now
sorry.
you're probably seeing the wrong thing. Huh?
No, still seeing the right thing.
Okay, great. So thanks, Johannes. So my name's Susannah Burrows. For those who don't know me, I'm a modeler with primarily expertise in modeling aerosol in global scale models. And I'm going to speak a little bit about where I think we might have some opportunities using Epcape observations to better understand how E3SM is modeling aerosol in this region, and how what biases we have and how they may affect our ability to simulate CCN. And I'm also going to try to talk a little bit about how we might be able to look at cloud impacts, and we'll get to that in a couple of slides. But first of all, talking about the aerosol representation, just as a little bit of background in E3SM, we represent aerosol as, so E3SM is DOE's Earth system model. It's a global scale model. We have to really simplify aerosol, so we represent it in 4 log normal modes, each of which is assumed to be fully internally mixed. 3 are soluble modes and 1 is insoluble. So these are sketched out in this diagram on the right from Hailong Wang's overview paper on these treatments in the E3SM V1. And we represent 7 chemical species, so clearly the chemistry is highly simplified as well. And these species are distributed in the modes depending on their size distributions and hygroscopicity. And then the model treats microphysical processes, including nucleation, condensation, coagulation, and resuspension, and also removal processes, including wet and dry deposition. And so clearly there is a lot of simplification going on here. And so I think a really interesting question that we haven't had maybe as much opportunity to look at as we would like is how do all these simplifications impact our ability to accurately simulate CCN? And so that's kind of the first science question that I wanted to briefly discuss is how much do these structural limitations impact CCN simulation? And size distribution chemistry and mixing state are some of the simplifications. And mixing state is one that's maybe really important for CCN, as shown in this paper by Zhang et al. In 2020 and a related review paper by Nicole Reamer in 2019, which shows that we really have a lot of regions where the aerosol is internally mixed and other regions where it's externally mixed, and that changes how the aerosol will activate as CCN. So to look at this in more detail, we need measurements of aerosol composition and size distribution and hygroscopicity and or CCN number concentration measurements. And I think one of the great things about Epcape from this perspective is that it will have all these measurements alongside measurements of cloud properties, which in some previous marine and coastal ARM campaigns was not the case. They had either one or the other, but not both together. So this gives us a chance to really look at this question. And so just to kind of sketch out an approach that we could use to do this, I think one way to think of this is that it's kind of a closure problem. So a closure problem involving both the observations, but then also a modeling component. And so we could start with the observations, taking observed size distributions and size dependent composition or hygroscopicity as measured during Epcape. And these are some examples of similar types of measurements from papers led by George Saliba while he was working in Lynn Russell's group in marine regions. And using those measurements, we can then calculate CCN numbers from the observed aerosol properties and compare those with observed CCN. So this is the typical kind of classic view of what a closure study is, and differences between those would be due to errors, or would be errors that are due to unobserved properties of the aerosol. Then to look at the modeling side, we can create similar size distributions and size resolves kappa from the model, and that tells us what the model would predict for those quantities. And we could do that in either E3SM's more simplified 4-mode treatment of aerosol or the more complex 7-mode treatment of aerosol. And so then, sorry, going back one step. And so then what we can also do is take these observed quantities of aerosol and project them into the E3SM size distributions and E3SM lumped chemistry categories to say, okay, if we took what we actually observed, but we represented it the way E3SM does, then how would that affect the CCN that we predict? So then we maybe could look at the differences between those two. So we look at the differences between the CCN from observed aerosol projected into MAMS modes versus CCN that's actually simulated by the model. And the differences between those two would be due to other simulation errors, for example, in the aerosol amount. And then we could also compare again between the model and the observations. So the CCN number from the observed aerosol properties projected into the model versus from the observed aerosol properties without that projection would be the errors that are really solely due to the model's structure. So I think this would be a really fruitful exercise. I don't know that this has been done before, and it would help us to really tease out which pieces of the model's structural limitations are contributing how much to our ability to predict CCN. So this is just CCN. It would be really interesting if we can go a step further and look at how does that actually impact clouds. A challenge, which I noticed Jerome Vast was just bringing up in the comments, is that global models can't resolve both all the cloud processes and also in particular the coastal effects in a region like coastal California where Epcape is going to happen. But I think there are a couple of possible strategies we could take here. One would be to take to use the information that we gained from the previous exercise about model observation discrepancies and prediction of CCN to make corrections globally to CCN in a model like E3SM or the CESM, and apply double call radiation methods in order to isolate the cloud droplet number response that would occur if we made those adjustments. So this would be similar to the approach that we took in this Science Advances paper, which I worked on with Dan McCoy in 2015 to quantify impacts of marine aerosol on Southern Ocean clouds through the first aerosol indirect effect. A second approach that could potentially be really fruitful, I think is one that's extending beyond my expertise and would really need to be a collaborative effort, is to initialize really high resolution or ideally LES simulations with aerosol conditions that have been developed either from observations like what we just heard in the previous presentation or from a 3D simulation, and then compare those with single column model from the E3SM, as well as comparing the responses when the models initialized similarly. And I just want to highlight that we're going to have some more discussion of opportunities for LES and SCM comparisons during a breakout session on Thursday morning, which Anne Fridland is kind of leading the sub part of that session where we'll talk about that topic. So then the second thing I wanted to talk about just really quickly that I think we can add from a modeling perspective is ways of thinking about the marine influence on an aerosol. So again, putting this figure here as a reminder that we have this marine and continental mixed influence and also air coming from the megacity. We have a bunch of different regions influencing the aerosols that will be observed at the site. And so in past studies, well, there are basically three categories of approaches that are used to distinguish between marine and continental aerosol. One would be using Lagrangian back trajectory analysis. So this example at the right is from some work we're currently doing in my group to look at the chemistry of ice-nucleating particles during the that were measured in parallel to the ACAPEX campaign or as part of it. And then the second approach would be to look at measures of anthropogenically influenced air from observations like measures of pollutants. And the third approach would be looking at measures of meteorological influence like the boundary layer structure or the humidity of the air. Previous studies tend to use one or two of these methods, but maybe not all three at the same time. And so it's often been a criticism of previous studies that are done at coastal sites that they are unable to distinguish between times when the air has more marine influence and times when it's really recirculated from the continent. So I think we could look at these three measures together and then see how frequently do they correlate, and then taking a more holistic view, look at how the cloud properties may differ between observation times that have been grouped by these metrics. And then finally, I have one more science idea I want to put forward. This one is more ambitious and more exploratory, but I think would be a really exciting thing to do if we can get the right team together to pull it off. And so I think the question here is, I also want to say this is something that Johannes Mollenstadt and I have been chatting about, and also others, including Sam Silva. So this has been kind of a gradual growth of this idea amongst us. And I think the thing we're really interested in understanding is, can we use observations in a more direct way to constrain parameters within models in a more statistical sense? And in particular, there's some previous studies that have shown that using measurements of the aerosol state and the CCN number can provide some constraints on simulation of the effective radiative forcing from aerosol-cloud interactions in models, but it's not a very large improvement. It's not a very strong constraint on those interactions. And so an interesting question would be, can we use Epcape to evaluate whether process rate observations such as the rain rate, which many might know is one of Johannes's favorite topics at the moment, can we use those to provide stronger constraints on the ACI than the state variable observations alone? And the approach would be to really build a perturbed parameter ensemble, ideally from high resolution models or a single column model, again, perturbed in the same way as I alluded to in the previous section, and then to use various observed variables as constraints from Epcape. So some that might be relevant here include the rain rate, the CCN number, total particle number, turbulence, and thermodynamic structure from balloon-borne sounds. I think this would be a really, really cool thing to do, and something I hope that we can talk about more. So thanks very much.
Thanks a lot, Susan. So our next speaker is Dan Lubin. So he's going to talk about Southern California cloud radiative properties. So Dan, take it away.
Can people hear me?
Yep.
Okay, I need to share my screen. Someone probably needs to release the screen sharing, or someone can display my slides for me. That's fine too.
Yeah, I think you can share the screen now. Yeah.
Okay. So let me try to go to my PowerPoint and go to slideshow. I'm using Zoom on a very old laptop and might be a little slow here, but hopefully I can catch up. Okay, can people see my slides?
Yeah, not in the presentation mode yet. Okay.
Okay, here we go. Perfect. Okay, so Lynn asked me to provide a review of California coastal clouds, particularly in the context of the radiative properties and the radiation budget. And in performing this little review, I discovered just how venerable a topic California coastal clouds are. It goes back easily, but by the time Epcape gets started, it'll be 100 years old as a topic. It's ultimately related initially to emerging naval aviation. San Diego is the home of naval aviation, and Scripps was involved almost right away with California coastal cloud studies. Of course, back in those days, the sectional aeronautical charts were nowhere near as complicated as today. So pilots like myself and Johannes probably would have had an easier time. But in any case, Scripps has been involved for a long time with California coastal clouds and continues to be involved. There are several climate researchers at Scripps who are interested in California clouds as related to Western hydrology, drought, heat waves, ecology, and also solar energy. So I think Epcape is going to be a very well received program locally here because of the local interest regarding climate issues in the West. And then, of course, California Stratocumulus were among the first studied with emerging remote sensing technologies and need for model improvements, in particular the Fire 1 experiment back in the late 1980s. And then we had the first AMF deployment, which is, as Mark Miller alluded to, is quite a confidence builder for what we can expect from Epcape. And there have also been several aircraft campaigns focusing on ACI, and there's a paper by Sarushian et al., which pools all of these data sets together in a unified database. So this is a very venerable topic, but clearly there's still a long ways to go. So I'm just going to just review some of the early literature, starting with the climatology. Of course, a common feature is the increase in the cloud amount during the summer as opposed to winter, from some of this earlier work like Klein and Hartman. And then the diurnal variability, which tends to have maximal cloud liquid water content in the morning, and the clouds tend to dissipate and then become optically thinner in the afternoon. This is just a schematic from one of the earlier papers on the various mechanisms that sustain the clouds. Some people have gone further and done harmonic analyses of the diurnal amplitude, which is a consistent feature of California stratiform clouds. The diurnal amplitude in both the effective radius and the cloud liquid water path. And again, we tend to have a maximum of both these quantities in the morning, tending to decrease throughout the afternoon. And then the variability with effective radius versus optical depth. This is another earlier study, ultimately based on Fire 2 data and also satellite or Fire 1 data and satellite remote sensing. And it's found for most of the thin clouds, there's usually a straightforward power law relationship between optical depth and effective radius that's indicative of cloud effective rate of cloud number concentration increasing with altitude throughout the cloud, according to some fraction of the adiabatic lapse rate. Ship tracks were one of the earlier modes of studying aerosol cloud interactions. A lot of ship track work was done. in California clouds. And this is one example, another earlier paper using aircraft in situ measurements of the droplet size distribution, and then multispectral imager data over the cloud. And we can see during the little ship track events, there's a decrease in the effective radius corresponding to an increase in the cloud albedo at visible wavelengths, the nadir radiance above cloud, and then a decrease at the near infrared wavelengths that's consistent with the change in particle size. And then the properties of the seasonal properties have been studied quite thoroughly now, with basically higher cloud amount, but lower clouds in summer, and lower cloud amount higher cloud altitudes in winter. This is just this figure summarizes what was in the earlier slide there. And this is ultimately just, it's related to basically the greater inversion strength in the summertime versus winter. And then this is one of my favorite papers on the topic, and Mark quoted from this paper as well. It's Allison and Mikael's paper based on the MASRAD data, showing the kind of things that we can derive using the ARM AMF data. And these are the histograms of cloud properties such as liquid water path, optical depth, effective radius that come from the radiometric measurements that the AMF offers, and then the CCN concentrations, and the scattering and aerosol index quantities that come from the nephelometers. And I think this is a figure that gives us confidence that that Epcape is going to be able to go much further with this. I think this he or she is derived the Aerosol-Cloud interaction parameter, plotting the radiometric derived quantities against the aerosol observing system quantities, and she shows that with the MASRAD data, the Aerosol-Cloud interaction generally appears with statistical significance. So turning to a lot of the research that's going on at Scripps that's of interest to Western climate issues. Rachel Clemesha here at Scripps has shown that there's a northward progression in cloud amount throughout the summer. And she relates this to subtle shifts in the lower troposphere stability and sea surface temperature trends that evolve from spring into summer. And this ultimately results in cloud amount shifting northward from, say, June through August and then into September. And then there have been some multi-decadal trends in cloud base height, ultimately related to increasing urbanization. Another paper with some Scripps authors. These blue curves at the left they represent the trends in the lowest cloud altitudes, the lowest cloud layers, and the brown curves are the remaining higher cloud layers. Generally, an increase in cloud base height over several decades as a result of urbanization and increasing temperatures during nighttime, affecting the dew point and raising the condensation level for cloud formation. And so finally, this is my last slide here. Lots of research going back again 100 years or so, having to do with cloud properties, remote sensing, aerosol-cloud interaction, but not a lot on what I'm most interested in myself, which is the actual surface radiation budget under clouds as it affects surface heating, heat waves, and also solar energy, which is a key topic of interest here in Southern California. As you can see from the data of this paper, these papers are just emerging on radiation under the California clouds. And this paper is done by an ecologist, so there's some strange units, the symbol K for shortwave flux, and then these photosynthetically active radiation photon flux density units, which I never quite understood. But ultimately, this is basically the surface energy balance plot. So we have the shortwave, and then the top panel, and the middle panel is the long wave component, and then the total energy balance in the red curves in the next to bottom plot. So there's not a lot of research on the radiative effects, the ultimate radiative manifestations of the cloud properties, and that's what I hope to be be involved with Epcape. I think that'll be my primary role. So kind of a short introduction here. I'll stop there and answer any questions.
Great, thank you, Dan. And yeah, the sectional chart brought back fond memories of flying in San Diego, which is where I got all my training. Great. So with that, thanks to all the speakers. I'll turn it over to Lynn at this point to start the discussion.
And I just want to also thank all the speakers. Great job, and thanks for keeping on time. That was awesome. And as the audience can see, there's a lot of different and varied interest in the science associated with Epcape. And there's been already a lot of suggestions in the chat for expanding the project, and we are completely open to that. So, and are happy to support any ideas you have. So feel free to bring them forward. And with that, I will hand it back to Dia and Johannes to continue the discussion and to circle back to some of the questions for more discussion.
Yeah, so I think our plan is mainly to hand it back to the speakers and to the audience because there have been some great questions in the chat. And maybe we'll start with Matt, so the first talk, and the potential applications of Lagrangian tracking of the clouds, and then, well, clouds and aerosol, and really getting very tight constraints at the endpoint or the starting point of the Lagrangian trajectory. And I saw that Matt and Rob Wood and Yutang Zhang and David Panemal have been going back and forth in the chat. So do you want to share share your discussion with the rest of us?
Sure. So there was some discussions around how we can constrain the cloud response to aerosols, and by looking at timescales on these adjustments for the liquid water path. And Rob made a suggestion of using similar liquid water paths but different effective radius in the clouds to track them over a day. And I think this makes sense in the context of looking at the Toomey effect, which assumes that the constant changes in liquid water path. So if you're starting with a similar baseline, that might make for a useful way to analyze the time response. And then one thing I hadn't fully appreciated is that there is a known bias in the cloud top retrievals from satellite of the effective radius compared to what ARM can measure from the ground looking up at these clouds. You're looking at essentially different layers of the cloud. So that's a very useful suggestion by Zibo and David Panemal and so on.
Yeah, and I want to pick up on Rob Wood's point that the timescales at which these cloud adjustments happen can really tell us a lot about processes, I think. So I think that's also one of the, well, it's a very useful thing to be looking at in observations, and I think it's also one of the ways that we can really constrain models, because just looking at the cloud state overall isn't going to tell us very much. But if we can see things happening on different timescales, I think that can at least tell us about Toomey versus rapid adjustments, for example. So I don't want this to be restricted to just comments that have already been made. So I think if people want to just free form enter the discussion, please raise your hands and we'll get to you. And also it's not just questions, it's also we also welcome comments, of course.
Yeah, I think there is an interest of or a discussion of deploying the Titan balloon sounder systems at the pier or somewhere else relevant could be useful from a flight, and also Mark Miller. So and also Lynn respond to that. So I don't know if either of you wants to discuss some of that.
I can, Lynn, I can just probably say a few words, and So we have discussed that, and we think that would be really cool. The problem we see though is that this is a little like this reminds me somewhat of trying to plan for flight planning for mass rad, because the limitations on this airspace are very significant, and it is possible to get things like this to happen, but it does take a lot of work. So I guess the thing is, gosh, I really hope we can do it, but I'm not sure. It's going to take some work to figure that out, actually, and I think it's going to take some meetings with the FAA based on past experience in this kind of heavy airspace region. The same thing was true in a sense in Cape Cod. So I think it's one of these things we'd really like to do. We're just going to have to see if logistically it's possible to work it out.
Yeah, thanks, Mark. And I'll just add that there are some very preliminary efforts to try and secure a large research vessel that might have the space for launching the balloons as well, if that's technically feasible. So, which might get them a little more offshore and out of the more complicated airspace, as well as the footprint for the launching of the balloons are things we've are trying to figure out a good location for.
Do people have a good idea of what payload you want to see on the TBS? If you could deploy anything you wanted, what would that look like?
I know what I would like to see, but I come at it from a slightly different angle. I would of course want one of the biggest problems we run into at ENA and in many other sites is that we really can't quantify easily the thermodynamic profile between soundings. Even though we do have remote sensing techniques that do a fairly good job at this, when you get to this kind of cloud system where you really have, when you get to the cloud top here, you're going to, if it's anything like mass rad, we're going to be looking at monster inversions over a very, very short area. Now, I don't think the tethered balloon can get all the way up there all the time, but one of the things I think that's really always been an issue with any of the sites where we do this is basically being able to get thermodynamic information. So for me personally, while I would love to have a ton of information about cloud microphysics and other things, the first line thing for me is just tell me what the temperature, humidity, and pressure and winds look like, and the winds less than the pressure, temperature, and humidity, and I'll be very happy with that.
Maybe a small drone would do that.
That's one of those things again where I wonder what, I can speak from some experience here at Rutgers University trying to fly a drone over our site, and it was okay about two or 3 years ago. Everybody was happy and nobody had a problem, and all of a sudden we got a directive from the university, no more drones, and now there's a big permission process. So I'm guessing we could do that, but it's going to come down to whether Scripps is, what are the limitations for not only for Scripps, but for the area in that. There are a lot of limitations these days when you fly these things, at least in the urban area where I'm at anyway.
Apparently there's a tethered balloon temperature sounding system where it's deployed along the cable, and I think it uses some kind of, fiber optic cable type approach, and it can instantaneously measure the entire temperature profile all the time at all levels. I don't know who's developing it. Is it Sandia? I'm not sure.
That's the DTS system, and there's quite a few people who are using it, but we use it with the tethered balloons on at Sandia. It's probably what you're thinking.
Yeah, that's what I imagine.
Proposals for putting it on towers, and then at SGP, Pierre Gentine had a underground and above ground horizontal version of that.
Yeah, I agree that temperature and humidity profiles are pretty basic. I was also excited to hear about the new aerosol sampler that's being designed for the TBS, so that could be great as well. I think we'd end up wanting multiple packages, so it depends on what we choose to target. So, the call is coming out soon, right, Nikki?
We're working on a call. I don't know if Jim's considering putting this one in the one that's coming, so don't quote me on that. And are you thinking of the stack measurement?
Yeah.
Okay, yeah. We've been, that one I believe is slated to go on quite a few missions because they shrunk it down quite a bit. So I think that's a reasonable one to be excited about.
Great.
If I, may I jump in here for a moment?
Please.
Well, just going back to this question of adjustments, which we had some interesting discussion on, and trying to tie it back to Mark's comment, if we see adjustments or changes, let's call them changes in liquid water path, I think it is going to be really important to have a very good understanding of the temperature humidity structure to see whether we are seeing liquid water path changes that are simply, due to meteorology, or in response to aerosol. There's, a big difference between the correlation between aerosol amount and liquid water path and the actual response of the system when you change the aerosol, and in that context when you change the meteorology. So I think that is something we need to think about if we want to really address these adjustment timescales.
Yeah, and I was thinking, so one thing that Mark brought up was the subadiabaticity of these clouds. I think mostly in the context of drizzle, but I think if we have measurements of the subadiabaticity and we can try to figure out what part of it is from precipitation and what part of it might be from enhanced evaporation due to aerosol, that would be a very nice measurement to have. Well, it's not really a measurement, nice analysis.
Though that evaporation could be through entrainment of air and unrelated to aerosol. So
yeah. So it requires understanding the thermodynamics and the meteorology very well. But I guess if we have in situ measurements of the free troposphere, that's going to help a lot.
Johannes, can I ask a question? If we want to get at subadiabaticity, how accurate do we need LWP? How accurate do we need the cloud boundaries in order to get there? I mean, I think we kind of have to look a little bit backwards to say, is this even possible? We may need LWP to better than 5 grams per meter squared, and then the cloud boundaries to something better than maybe 25 meters if we want to really get it well. I don't know. Do you have a sense?
Yeah. I think I think the cloud boundaries, we should be able to get at least, where we have the ground-based instruments, because we can get the cloud stuff from radar pretty well and the cloud-based from LiDAR pretty well. That's my feeling. And then LWP, I guess, might be the limiting factor. And I guess it also depends on probably the cloud type, right? So it's a very good point. I mean, it's something that we need to look at before we wade into it. But if it can be done, then I think it would be a great thing to have.
Yeah.
Well, we can get LWP to better than sort of 10 to 15% relative uncertainty over the whole range if you combined the area and the microwave radiometer. A different question would be, is a single site at the end of the pier enough? What type of sampling error do you have when you're looking at these type of cloud fields if you only have a single site?
Yeah.
So that would be a separate question, and whether or not we need additional sites either inland a little bit or elsewhere.
Yeah. And one of the things that really attracted me about this proposal when I first talked to Lynn about it was the ability to do remote sensing from the pier and in situ sampling of hopefully a somewhat similar cloud a kilometer-ish away.
Another question is, can we use the scanning radar to get at some of these questions of how representative the pier is? I mean, we'll at least be able to see hopefully some of the kind of mesoscale variability in terms of cloud top and inversion height.
Yes, I think that's one of the things that's a real advantage of having, Soledad there and being able to look out over this, because one of the interesting things is that, we still have to ask ourselves, back to Dave's question a little bit on this too, is, the spatial part of this, I still wonder, you know, we probably might not be completely devoid of coastal influences at the site, even though it's out there quite a ways. And you can sort of see that in some older modeling studies that we did. But I also want to speak to Dave's point for one other thing too. One of the things we had, and I think you probably remember this, Dave, was during MassRad, you know, we had such small liquid water paths sometimes, and we early on had wet window problems that were, you know, that they're gone now. We don't have those, but your point is a really good one. I mean, this is going to, you know, how we get these liquid water paths and how we understand them, and using the scanning radar to possibly bridge some of that might be, you know, one way forward. But I think you're really right about that. And in that Microphysical paper too, if you look at that, there's a comment on there about the fidelity of the aerosol-cloud interactions when you don't have a lot of subadiabatic behavior. And these clouds don't drizzle all that much. So it's going to be, at least the ones that we've looked at MassRad don't. Maybe these do. We'll have to find out. But I think a lot of these questions, you know, these are really good questions, and they all come back to that issue of what is the liquid water path and how well can we constrain that, and how well do we know it.
Michael, did you want to add something? I saw some stuff from you in the chat.
I was just I was responding to the conversation between Dave and Scott about getting the HER developers involved, and I think there's a couple of groups that will be doing some parameterization development and model testing and validation. I know Ann Ferdland in Israel. I think Israel's here, so maybe he can speak to the plans from the Penn State and GIST team. But Dave, I agree with you. It would be great to get Joe Olson involved in this, because I think he's thinking about stuff kind of on the same wavelength as us in terms of how do we capture variability, kind of a, you know, subgrid variability. And that's a tricky thing to do with a stationary ground site. So having another ground point up on the Soledad is helpful. And then also, I mean, this is to me, this is where the aircraft observations really become super valuable. I know we don't have that long temporal record, but just having some of that spatial context is really important.
Yeah,
Michael,
that was a real
Go ahead, Dave.
I was going to say that was always been a real challenge, the stratocumulus clouds in the HER, but we made real progress in the current version that's now operational. But we know we have a ways to go. So I know that I can tell you for sure, Joe and Graham and many of us in NOAA are working on this problem every day.
So Michael, I wondered whether you have plans to try to get a microwave radiometer on the Tuanota, because that would be exceptionally valuable.
Yeah, that'd be great. I mean, I don't know. So there's a whole bunch of radiometers floating around at NRL, and it's kind of a matter of finding the right person. But that would be an excellent addition. So I will
this discussion came up with Matt Lebsock, and I think it was the ACCP discussions. It doesn't really matter when, but Matt would be a good person, because I'm pretty sure JPL has developed some radiometers that would be really useful in this regard. And yeah, this took us back to discussions about the Eureka atomic experiment, but Matt would be a good person to start to talk to about this.
All right, Matt, you know where to find me on the internet.
Is he online?
He should be here. He was here earlier anyway. He looks like he stepped out for now, but I'll follow up with him for sure.
Okay, so I see that Paquita and Lynn have been talking in the chat about additional ceilometers, also as a way to get at the spatial variability, which I think might be a possibility.
Someone was mentioning also using arm radars for looking at the spatial heterogeneity out over the pier. I was having a look around. There is a WSR-88D nearby, and while in theory that's mainly looking at precipitation heavier than drizzle, one thing you can get from the WSR88D is some of the Bragg returns and insect returns can give an idea of some of the small scale variability there. I think bringing in something like that, in addition to the HER, would be a very good move as well for giving some context. Now, please excuse my complete ignorance in geography. Scripps is in just right near San Diego, right? Yeah. So there is an 88D fairly nearby, and I'm just looking right now, and there's not much blockage, so you should get good coverage out over the ocean there.
Is the question though how high it is and whether it'll even be able to pick up anything that low?
Yeah.
I mean, I know I also live on the coast, and we've got a radar up at about, I think, 2,000 feet, and it doesn't see any of the coastal stuff because it just doesn't scan out.
I'll check it out. It's KNKX. I'll have a look there.
Yeah,
it looks like at the moment we've got ducting, all kinds of weird stuff going on there, but yes.
Yeah,
that's a problem we've seen in other locations too.
Yeah.
The radar is usually too high.
Yeah.
That's at Miramar, so it's not terribly high up, but it is slightly away from the coast and something like 500 feet up, I would guesstimate.
But the part of my reason for bringing up her was listening to Mark talk about needing more frequent thermodynamic profiles there, and I wonder whether you can use her or something like that to kind of work out, how frequently do we need them? That's a really interesting question. I mean, could it be the case that, rather than talking about exotic things like fiber optics, that working with another partner, launching more soundings might even be a way. But also, can we look at something like taking that column out of the HER and using that as basically a background field and then nudged by observations as well? Now, it won't necessarily capture the clouds or anything like that, but it could capture a lot of information about the diurnal cycle and thermodynamic variability there.
I mean, the figure I showed from Ron and Mitchell, they were using the AMDAR soundings from commercial aircraft.
Yeah.
And there are a few hours in the early morning and late evening when there are no flights, because it's primarily a passenger airport there in San Diego. But yeah, so they were just comparing the AMDAR soundings over a long period of time versus the balloon soundings at Miramar. And because that's a military base, I'm pretty sure they do 6 hourly there.
Right.
They're doing a lot of the work for the Naval Air Station.
It'd be wonderful to work with maybe the local weather service or whoever's bringing it. AMDARs don't necessarily get archived, and you kind of need to know someone to get access to them. So having them archived would be a really good idea.
Mm-hmm. Yeah, especially since the San Diego airport is right there at the coast. Yep. So you don't have a lot of stuff in between. It's pretty much just Mount Soledad.
Yep. Representative.
Since we are sort of touching on modeling, so I guess when we put together this proposal, one of the questions was, why would you want to do something so masochistic from a modeling perspective as coastal a coastal site? And I think one of the big reasons is that, of course, it's very relevant to society in terms of the hydrological contribution from coastal cloud and coastal drizzle there. So since Israel is here, maybe do you want to say a few things about modeling strategy?
Yeah, I'm currently with a daughter. My daughter is at home because she's has some fever and so on. So I'm not 100% with you guys. I try my best. No, I do wish to note. First of all, regarding, you already saw that basically we have the MWR. We will have another instrument so we will have the 3-channel at the Pierre and the 2-channel at Mount Soledad. So, and obviously this is not perfect, but to give some sort of a distribution of liquid water path values over there, it would give us some sort of a rough estimate. Same thing for the Sackers that we plan to deploy them and have like RHI scans, sector RHI scans towards the pier. So therefore, we would be able to get some sort of a rough estimate of the distribution. And again, there would also be there is a possibility that we would eventually have the aegis array there. We would also have the aegis array there eventually at the pier, so we would be able to better constrain these retrievals, have something to compare them with. I know obviously it's very difficult to get to the accuracy of the area retrieval. Concerning the modeling efforts, yeah, so we have some thoughts, and I think this was already mentioned. I can't remember if it was in Susannah Burrows' talk, but again, using an SEM, doing and case studies with the Lagrangian approach, using one of the SEM, perhaps E3SM, CSM, mul E3. And so on. That's the main point at the moment. Our main goal is to look at case studies. So that's from our perspective at the moment. Obviously, there is a possibility to look at and evaluate global simulations, obviously with some instrument simulators, which I think will be highly useful for this deployment. Again, because we would have vertically pointing instruments at both sites. Obviously, this is within the subgrid scale, but it could give us some measure of subgrid scale variability, especially considering that the SACers would have also the vertically pointing mode. So we would simultaneously have LiDAR and radar observations at zenith. We could get some sort of like rough retrievals, at least at Soledad, and better constrained or lower uncertainty retrievals at the pier. Yeah, so that's it. Hope it helps.
Yeah, and I mean, I mean, it's obviously a subgrid problem for most models, and I think it will be very interesting to figure out, you know, what does the resolved scale need to be, and how advanced does the subgrid scale representation need to be for the model to be able to come up with meaningful results in this kind of complex orography. So Lynn, how much time do we need for the photo?
We could do it now if there's a lull in questions. So I'll hand it over to Verda. I think mostly we just need a smile at some appropriate time, and or if you want to hide, you can turn on, it'll record your name instead of your face. Verda, are we good to go?
Yes, there are 4 screens that I'll need to photograph. So everybody just give me a moment. All right, I'm going to start.
We'll get our pandemic memento. I say, could you imagine logging into this breakout room right now?
I guess we could keep talking during this.
Okay, we did have 4 screens. Now we're down to 3. So I've got everybody.
Great. So yes, last thoughts or comments from anyone? There wasn't much action on Slack, but if you think of things later, I think we'll have access to that channel going forward. So feel free to add more things there. Any other last thoughts? So keep thinking of ideas. We welcome them, and just let me know how I can support you.
Thanks, Lynn.
Thanks, Lynn.
Thanks, everyone.
Thanks, Jonathan. Dia.
Bye. And this is your
everybody soon.
enforced break before the posters. So see you at the posters.
Thanks, Lynn.
Thank
Bye.
you.
Lynn, I tried to download the discussions, but I'm having some.
I think Verda will take care of that for us.
Yes, we'll have a report with all of the chats unless they were private.
Okay.
And do you know where the recording will be posted?
I think that will be given to the sponsor and they'll disseminate the video and the report.
Okay. So to be announced. So we
Correct.
don't know yet.
Correct.
That's good.
Great. Well, thanks to our moderators, Dia and Johannes, and see you guys in the posters.
Pleasure. Yeah, this was a fun session.
Yeah. Yeah, well. Okay.
Can't find the button. Right.